Guys, so today's talk is all about Martian evaporite minerals characterization at Ritchey crater using CRISM hyperspectral remote sensing data. So this talk is a part of my first master's research, and I'm going to dive into this now. So when it comes to evaporite deposit, we are talking about minerals that are produced mostly of minerals produced by evaporation of saline solutions. So this kind of minerals needs water, and that water must be evaporated into the atmosphere for this kind of minerals to precipitate. So at this picture over here, it shows, the story behind evaporite minerals. So evaporite minerals, for the same process that I mentioned before to happen, the water input or the water body in general must enter a restricted environment where water input remains the net rate of evaporation. So the water here or the evaporation here occurs when water becomes enriched in salts, and these salts start precipitating when water becomes oversaturated. So here we can say that the crystallization of the salt minerals could lead to the formation of evaporite deposit. So here in this table shows some families of evaporite deposit, or let's say classes of evaporite deposits. So here they range from chlorides, they range from sulfate to carbonates, but all this precipitate indicate that the climate was arid and let's say hot, semi-arid and hot, right? So that's for evaporite deposit on Earth. But when it comes to Mars and how that relies to evaporite deposit in general on Mars as a planet, it's a medium-sized world, as you know, and its surface is always characterized by crater, and it's old. But the most important variable here is then atmosphere. So the atmosphere is mostly consisted of 95% of carbon dioxide. So I try here to mention I try to highlight, some information about Mars, but I'm trying just to give a little intro about this. But as I said before, the then atmosphere is mostly composed of 95% of carbon dioxide. The rest includes argon, includes nitrogen, with small portions of trace gases. And why I said the then atmosphere is important because it affects heavily on Mars surface. And this makes water quickly evaporated. So water here in our research is the most important variable. But there is one exception when it comes to salty water, especially in warmest places. It might take longer due to its saline content. So there are some research that suggests this. So for example, when it comes to this research that is done by Lang and Wong in 2010, it shows some kind of evaporite deposit called sulfate. So very sulfate, for instance, here are characterized by three important absorptions. So here we have an row absorption at 0.43. We also have two-port absorption between 0.53 micrometer to 0.70 to 0.86 micrometer. But here the most important thing is the exact position of these absorptions can be diagnostic and indicative of the presence of ferric sulfate and also magnesium sulfate. Another study here is done by Ray and many authors in 2010 as well. It shows some spectral locations of newly identified evaporite minerals on Mars valleys. But this kind of evaporite minerals that are relevant to Mars are hydrated, right? So here the most important thing is when it comes to this figure A, it shows spectra, and here figure B and C, the locations of interest samples, right? So here we have the sample 1 on this figure A that shows, how much is definitive and representative to the spectra here of basanet. While the second spectra 2 and 3 are not, representative, or let's say are less definitive of hydrated evaporite minerals like sulfate or alcin, but maybe it can belong to another group of minerals like zeolite. So that's why the objective of this research is to detect evaporite deposit on Mars. So what kind of this evaporite deposit? So we choose for this study to detect and characterize gypsum and salt. And why exactly gypsum and salt? Because this kind of minerals are connected to, to anhydrite soil. And anhydrite soil, if we find some proofs about it on Mars, it might help us to understand the water cycle existence on the red planet later in research. So we are using these following indices. So the first one, it stands for soil salinity and solidicity index. The second one is NDGI, is only focused on gypsum. It stands for normalized difference gypsum index. So these two indices are supported by remote sensing community. So the first research at left, it recommends to use this index to characterize salt. And why exactly is important? Because it discriminates different soil salinity levels, and it integrates the swear bands together to map, salinity accurately. The same applies to NDGI. Another research suggests right side by Robert Milovsky. So this index, it integrates as well like SSI, the swear bands, but at specific wavelengths. So here comes the rule of AI. It predicts exactly, the specific wavelengths we need to predict and to map, gypsum on any space on Mars, or any place on Mars in general. So that's the whole objective of this research. And we want to apply this on an example of Mars. It's not on the whole planet, but just on one place on Mars. So these indices are not coming overnight, but they are implemented and developed, but also they are validated through land terrestrial examples. And one of these examples is Omongwa salt pan. It's a salt pan located in the east of Namibia. It's about the size of 20 kilometer square too, and it's characterized by semi-arid, hot climate, and with an average temperature of 20 Celsius. So this is just a satellite imagery of Landsat 8. It shows exactly where this case study is located. So we choose Omongwa salt pan for pseudo validation because we want to apply the following dimensions to indices on this side before we apply them on our example on Mars. So the result obtained shows this result over here. So I want just to explain a little bit this palette of colors. So the red values here, red, orange, shows the high dominance of the mineral. When it comes to purple, cyan, or blue, that's just the low dominance of any mineral detected on this side. So here it comes the dominance of gypsum on Omongwa salt pan. So it shows that both indices, SSI and gypsum index, have mapped almost similarly the dominance of gypsum and salinity on Omongwa salt pan. But maybe at left, when it comes to gypsum results, it maybe indicate that gypsum index further highlight just the content of gypsum, right? But while the right figure here, it's about salinity index. So it shows some greater sensitivity to salt and all evaporite minerals. It means the salinity and solidicity index focuses only on salt, while gypsum index focuses only on gypsum. So salinity index, it highlights everything about salt, and gypsum index, it focuses and highlights just on gypsum. So once we apply this on Omongwa salt pan, we are ready to do this on Mars. So as I said before, we are going to choose one example, and this example is Ritchey crater. It's a fresh crater, and it's located in the middle of Hesperian rigid plains and Northern highland terrains. So this crater is about 79 kilometers in size. And why choosing for this study? Because it has some indications, and many scientists have found several kinds of minerals that may indicate that water may have flowed in the past of the red planet in general. So Ritchey crater, the data we got from, yes, it's from CRISM in general. So it's a compact reconnaissance imaging spectrometer. It's the tool that we got our data set. So it's a visible infrared hyperspectral device. It operates in general from 0.4 micrometer to 4 micrometer. It means 400 nanometer to 4,000 nanometer. So this device is really important because it measures the spectrum through 544 channels. And the good thing about this device, it has a good resolution in 18 meter at an altitude of 300 kilometers. So this device consists of three main components that compose its hardware. So here we have the OSU. So the OSU stands for Optical Sensor Unit. So this unit, it consists of gimbals and optics. So this optic and gimbals are controlled by GMA, which is shown here. So this GMA is, let's say, it controls these gimbals and optics just to allow observation at multiple geometries. And also the most important thing is to remove the snare that caused by spacecraft motion. We also have another, let's say, the hardware of CRISM is DPU. So this device stands for data processing unit. It's really important because it sends data from the OSU, which stands for optical sensor unit, to the spacecraft. So this is important because it controls data acquisition, pixel binding, and data editing as well. So CRISM has, data that comes from CRISM in general is, is compressed, right? And it's extracted in many directories. So these directories, it differs from the resolution from the observation mode. So our interest directory here in the study is TRDR. It stands for Targeted Reduced Data Records. So this directory, it comes divided into two spectrums. We have visible near infrared spectrum, which is called S cube, and then we have another cube called L, which represents the infrared bands. So this is just a little representation of this directory. It's characterized by class type. So we choose the class type is FRT, is full resolution targeted. So this class, it measures the spectrum through 544 channels and has a resolution of 18 meter in an altitude of 300 kilometers. So this data set is really important for our study, and we combine this with another kind of data set. It comes as well from Planetary Data System, is the provider of our data set in this study. So we come up with another sample of CDX's context camera sample. So we are using this kind of data for georeferencing our area of interest, and also to get some coordinate that we need to project, our area of interest to do some pre-processing steps later in research. So that's just a lookup of our hyperspectral sample of Ritchey crater, and here just a 3D cube of visible near infrared band. So this built using NDGI software. Here the methodology of our research. So in order to divide this, but this full chart, it shows the whole research, the walkthrough of whole research. But in this presentation, I'm not going to make it longer. I would like just to focus on the most important part is the infrared section. So here, all cubes, it comes from PDS CRISM data, is the Planetary Data System, so it's available for free. So we choose the RDR directory and observation mode and class type full resolution targeted. So the data, it goes through a process called correction. So we have two corrections. We have photometric correction and atmospheric correction. So photometric correction is used in the study for calibrating data to apparent reflections, and then we apply atmospheric correction for removing the bands of carbon dioxide absorptions. So then data, it goes through another process of georeferencing, image registration, and then we project this in order to process our data and apply our indices so that we can compare our results to Earth examples, to Earth spectra, and other findings. So here, all this process is done by, okay, so it works good. So this walkthrough is done by a programming language called IDL. Then we try anyway. So I'm going to just get back to this. So this is just the tool we developed. So it's already developed and maintained in general for the PDS data processing. So yes, this tool is developed in purpose to do projection, to do correction that I mentioned before, atmospheric and photometric corrections. I don't forget here, this tool is very useful for doing data cleaning and filtering. So another tab here in VS Code, it shows another code I'm working on for merging the visible near infrared and infrared cube into one single image. But this one is just for CAT. In general, the tool is called CAT, and it's used here. So I'm just trying to show you here, this in VS Code. So I try to implement this in NDGI software, and this shows some kind of errors. Anyway, so the tool finally is implemented successfully on NDGI. Maybe it has a poor looking design, but the most important thing is the features are working as we expected. Right. So I'm going just to fix this. So we get into the pre-processing walkthrough. So the first step is converting the PDS data to CAT format. So planetary data system comes, as I said before, compressed and extracted into linear directory. So we need to convert this to the tool that I showed you before that is developed called CAT. So we want this data to be, responsive to this kind of tools, which is CAT. So here we have PDS data. It comes in reverse order. So it starts from 4 micrometer to 1.5, which doesn't make any sense. But once we try to convert this, everything has been changed. So you see here, the reverse have been reversed from short to long to long to short, right? And the good thing here, this CAT tool is going to allow us to apply many functionalities, including atmospheric correction, including photometric correction, data projection, data registration, and more properties. So the second step is converting the CAT format to be applicable by photometric correction. So we apply photometric correction once we convert data from PDS to CAT. Why this correction is important? Because it's going to calibrate data to reflectance or to non-apparent data radiance. And this is important for the study because it's going to have an accurate, radiance for non-solar incidents. So the second correction here, or maybe let's talk a little bit about this, because here we will see another change. If we take a look at the spectral profile, the amplitude of the spectra have been changed from 0.08 to 0.016, I think. And then we apply atmospheric correction. And here's the challenge of our study, because everything have been changed completely here. You can see here this deep absorption at 2000 nanometer, but then it disappeared because of carbon dioxide absorption band. So we are trying to apply this kind of correction just to have a better result at the end. But we can't get rid of this, and we can't keep just photometric correction. It's not going to affect a lot on our results, but we need something more important, is CIRRUS algorithm. So what is CIRRUS algorithm doing? It applies some filtering and cleaning, functionality. So it's going to describe and rectify the congregation of the data in general. And you can see here how we see some kind of smooth here. So the pixels, the spectral profile, it's very smooth here at left compared to the data before we apply CIRRUS algorithm. And then at the end, we have another pre-processing step, is registration and projection. So we want to register and project our data just to have a meaningful, representation of data in general. So we first start with building GLT. It's GLT something we have in general. So you can see here the process, just in detail, and then we applied this for projecting the whole the whole lookup in general of our area of interest. And then I'm trying just to show you the results once we apply the following indices I showed you before, NDGI and SSI. So here the result shows this. So at left, we can see that data is not are not applied by filtering algorithm, but after we apply enhanced list filter using NDGI software, you can see the data are represented much more better than the left one. So you can see here, you know, NDGI, the gypsum dominance along the left side of the sample of Ritchey crater. You can notice here that gypsum or index in general, it highlights only the gypsum content compared to SSI findings. So salinity here as well, it have mapped the same way as NDGI do, but the problem here, it shows all, you know, it shows some kind of sensitivity to all evaporite minerals. So as you can notice here, after we do filtering, you can see if we try just to compare a little bit the gypsum findings with salinity findings here, it highlights everything, everything about salts, about evaporite minerals. But when it comes to NDGI, it shows only gypsum content. And that's why I said before, gypsum index is only for gypsum content. But when it comes to salinity index, it shows sensitivity. It tries to detect everything related to salts, right? And gypsum is a part of the evaporite deposit. That's why we see a conflict here. So if we try to test a little bit our data set here, we try to focus on all the spectral profile from all detected pixels. So from purple here, we see a spectral profile of purple, the cyan and blue pixels as well. I try to extract them, and the red and cyan and orange pixels as well. There are some spectral signatures concerning this you know, this dominance here. But the most important pixel here is the red one because it shows the high dominance of gypsum in this area of Ritchey crater. And here, I think all of them are characterized by strong absorption at 2000 nanometer. We have some weak absorption as well at 1.4 to 1.7, but the strong absorption here happens at 2.1 or let's say 2000 nanometer in general. The same here for SSI, we see another conflict.
You have to come to an end, Lang. You have to come to an end.
Yes, okay.
Yes, but you can finish, but talk a little bit faster.
Yes, okay. Right, so here the SSI index, it shows the same results, so the same absorption as well at 2.8 micrometer. So here, as I said before, the greater sensitivity of SSI has applied as well to NDGI index. So here I try just to compare my findings with some Earth Spectra from USGS laboratory spectral of gypsum. You can notice that the result is a little bit accurate. We have also the same absorption here at 2000 nanometer, the same here at 2000 nanometer. We have some little kind of absorptions here, and the same I did for Khalid. So I can compare that with USGS spectral library. I found something very accurate. So there is an absorption here. Maybe this one looks more deep compared to that one, but this can give some kind of impressions that our research findings are going on the right path. So here I come up with another comparison I did for my findings, but this time focused only on salinity. So this browse product, I found it from CRISM, so from CRISM Planetary Data System website. So I try to compare here the dominance in general. You can see here the highest value, which shows in red. This also here applies, which shows on orange. And so you can see here the same palette of colors. So we have the low values as well here as cyan. Here also we have cyan. We have here, you know, yellow. It shows here some kind of low and low dominance of salinity in orange. So it means that everything is going to be accurate and everything is on the right path. So that's all about, you know, the research. I'm trying to speak here, sorry, just for concluding my research. So I could conclude that my research study is, or the obtained results indicate that both indices have mapped, evaporite minerals similarly. Maybe NDGI highlight more the concept of gypsum, while SSI focus only on, and let's say it was very sensitive to all evaporite minerals. So this result in general show that these areas are characterized by some kind of textured soils forming fine smooth crust. So that's for my, just some appendix. So I'm going to post soon on my GitHub the code I'm working on to merge the both cubes. And also here there's some website to learn how to set up CAD and how to implement it and integrate it in NDGI software. So this is just the website to get PDS data and another tool, Java-based tool for viewing present data and spectral files. And this is just a map-based interface. You can visit this website to know more about it. So that's for the references, and thank you.
Okay, thank you for this lecture. I have here a question from Holger Eisenberg. He once tried to create visual light images from CRISM data, but found it in the visual light spectrum very noisy. Have the filter degraded during Earth to Mars transfers in that spectral range?
So I'm trying to read the question. So I found noisy. Yes, so it might happen because of data processing walkthrough, because PDS resource in their website, they recommend to follow the walkthrough. So the first step in the walkthrough is converting PDS data to CAD, and then we should apply photometric correction, then atmospheric correction, then we should start cleaning and filtering our cubes. So I think the reason why you see the degraded, the filter degraded during Earth to Mars transfers, that spectral range, just because of maybe the data pre-processing issues.